Right now, at this very moment, you are trapped on the only planet humanity has ever called home. Everything you've ever loved, everyone you've ever known, exists within a bubble so infinitesimally small that it's practically invisible to the universe. But what if I told you that the nearest star to Earth, aside from our sun, is still so catastrophically far away that it would take our fastest spacecraft longer to reach it than humanity has existed as a species? In fact, crossing just 1 light year, the distance light itself travels in an entire year, would demand a sacrifice of time so profound that civilizations would rise and fall during a single journey. Empires would crumble. Languages would die. Everything you know would become ancient history. Today, we're going to explore the brutal mathematics of interstellar travel, the technologies that might one day carry us across the void, and the horrifying truth about just how isolated we really are in this cosmos. Welcome back to Orbit Unknown. This is the story of humanity's greatest challenge. Hello everyone. Welcome back to my channel Orbit Unknown. Today we are fascinating the very interesting how long would it take to travel 1 light year? The truth will shock you, part 2. Understanding the scale. When numbers lose meaning, let's start with something most people get wrong. A light year isn't a measure of time, it's a measure of distance. Specifically, it's the distance light travels through the vacuum of space in exactly 1 year. Light moves at 186,000 miles per second. That's 670 million miles per hour. In 12 months, traveling at that incomprehensible speed, light covers a distance of approximately 5.88 trillion miles. 1 light year. To put this in perspective, our sun is only 93 million miles away. We call that distance 1 astronomical unit, or AU. The entire solar system, planets, asteroids, comets, everything we consider our cosmic neighborhood, fits within roughly 50 AU from the sun. 1 light year equals 63,000 AU. Our nearest stellar neighbor, Proxima Centauri, is 4.24 light years away. That means the light we see from that star tonight left before humans invented electricity, before cars, before airplanes, and it's still the closest star to us besides our own Sunday. This single fact should terrify and inspire you in equal measure. Part 3. The current state of human spacecraft. Our snail's pace. Here's the stunning reality. Humanity's fastest spacecraft is the Parker Solar Probe, launched by NASA in 2018. It's designed to study the sun's atmosphere and has achieved speeds of 586,800 kilometers per hour, approximately 364,000 miles per hour. That sounds fast, revolutionary even. It's 0.064% the speed of light. If, and this is a colossal if, we could somehow maintain that velocity indefinitely, without stopping for fuel or repairs, with no acceleration or deceleration, traveling in a perfectly straight line toward Proxima Centauri, it would take us 6,600 years to arrive. 6,600 years. The Roman Empire lasted about 500 years. Ancient Egypt existed for 3,000 years. The entire span of recorded human history is only 5,000 years. A one-way trip to our nearest star would consume more time than humanity has had written records. And the Parker Solar Probe is specifically designed for high speeds near the sun. Any spacecraft carrying humans or advanced equipment would need to travel slower for safety, reliability, and fuel conservation. The more realistic speed for an interstellar vessel? Somewhere between 10% and 20% of light speed. Even at 20% light speed, which we have absolutely no technology to achieve, reaching Proxima Centauri would require 21 years of flight. But here's what the physics textbooks don't tell you. Maintaining that speed across the vacuum of space requires solutions we haven't invented yet. Part 4. The physics problem. Why fast is impossibly hard. Getting to space is one challenge. Getting to relativistic speeds, speeds approaching the speed of light, is an entirely different nightmare. First, there's momentum. A spacecraft carrying humans needs enough mass for protection, life support, food, water, and fuel. More mass requires exponentially more energy to accelerate. Einstein showed us that as you approach light speed, the energy required approaches infinity. You would need to convert entire planets into fuel just to reach meaningful interstellar velocities. Second, there's the problem of interstellar medium. Space isn't empty. It's filled with dust particles, hydrogen atoms, cosmic rays, and debris. At relativistic speeds, these particles become deadly projectiles. A speck of dust would hit like a nuclear explosion. Your spacecraft would need shielding of impossible thickness. Third, there's the fuel paradox. Any rocket carries fuel for acceleration. But if you're accelerating for years, you need fuel to carry fuel. The mathematics quickly become absurd. You'd need a fuel mass thousands of times larger than the spacecraft itself. Fourth, and most chilling, interstellar distances mean you're traveling blind. At 20% light speed, you have only about 15 minutes to detect an object ahead and change course. There's no time for evasive action. A collision with a rogue asteroid would obliterate everything. This is why physicist Carl Sagan famously said that interstellar travel isn't just difficult. It's fundamentally hostile to everything we understand about physics and engineering. Part 5. Breakthrough concepts. Scientists think they have answers, yet scientists refuse to accept defeat. Over the last 50 years, a handful of brilliant minds have proposed radical technologies that might, just might, make interstellar travel possible. Project Orion, conceived in the 1950s, proposed riding a series of nuclear explosions to accelerate. The idea was horrifying but theoretically sound. A spacecraft with a massive shock absorber could detonate nuclear bombs behind itself and surf the shockwave forward. This could theoretically reach 10% light speed. But the practical problems, radiation exposure, structural integrity, international law, made it politically impossible. Antimatter engines are another concept. Antimatter annihilates normal matter, converting 100% of mass into energy. A spacecraft powered by antimatter could theoretically reach 90% light speed or beyond. The catch? Producing, storing, and controlling antimatter requires technology we don't possess and energy resources beyond our current comprehension. We've never created more than microscopic amounts of antimatter, and storing it would require fields that consume more power than our civilization produces. Then there's the ion drive, which we actually possess. Ion drives accelerate charged particles to extreme velocities for propulsion. They're incredibly efficient and can achieve speeds of 200,000 miles per hour. NASA's Dawn spacecraft used ion drives to explore the asteroid belt. For interstellar travel, you'd need ion drives operating for years, with power sources far beyond current nuclear reactors. But the most fascinating concept is the solar sail, a massive sheet of reflective material that catches photons from the sun or a powerful laser. As photons strike the sail, they transfer momentum. This requires no fuel. A sufficiently large sail could accelerate indefinitely, theoretically reaching 20% light speed or higher. The Planetary Society has proven this concept works on small scales. Larger applications are theoretically possible. Each of these technologies pushes against the absolute limits of what's physically possible, yet none have been proven viable for human travel. Part 6. The Time Dilation Mystery. Relativity's cruel gift. Here's where interstellar travel becomes truly strange. Einstein proved something that still confounds most people. Time itself moves differently depending on speed. If a spacecraft could somehow accelerate to 99.9% the speed of light, something extraordinary would happen. To observers on Earth, the spacecraft's clocks would appear to slow down dramatically. A trip to Proxima Centauri at near-light speed would take Earth observers over 4 years to complete. But to the crew aboard the spacecraft, time would compress. Due to relativistic time dilation, the journey might feel like only several months to them. While decades pass on Earth, the astronauts age only marginally. This is the universe's cruelest trade-off. Yes, relativity allows faster travel through subjective time. But the energy requirements to achieve such speeds are so astronomical that you'd need technologies that border on science fiction. Most theorists believe that truly practical interstellar travel will be limited to 10 to 20% light speed. At these velocities, time dilation barely applies. The journey would indeed take decades for both the travelers and everyone on Earth. Consider, launching a mission to Proxima Centauri at 10% light speed means you won't see results for over 40 years. The crew will age 40 plus years. Everyone you know on Earth will likely be dead when you arrive. This psychological reality might be the biggest barrier to interstellar exploration. not physics or engineering, but the human unwillingness to embark on a voyage that exceeds a human lifetime. Part 7. The Generation Ship Solution. Humanity's slow exodus. Because single lifetime travel to other star systems appears impossible, scientists have proposed generation ships, massive spacecraft designed to sustain human populations for centuries. Picture a spacecraft the size of a small city, containing thousands of people, agriculture, water recycling systems, power plants, and everything needed for human survival. This ship accelerates slowly, maybe reaching only 5% light speed after decades of acceleration. It then coasts through space for centuries. The people who embark never reach the destination. Their children don't. Neither do their grandchildren. But perhaps 10 or 15 generations later, descendants of the original crew finally arrive at a distant star. This concept raises staggering challenges. How do you maintain genetic diversity across 500 years? How do you prevent technological degradation? What happens to social structure and government over centuries? Will future generations even want to reach the destination, or will they consider the ship their true home? Some scientists propose even stranger solutions: suspended animation or cryogenic sleep. Freeze the crew and wake them upon arrival. But biological systems degrade in freezing. We still can't revive humans from cryogenic suspension. Others suggest digital consciousness transfer, uploading human minds into computers that operate the spacecraft. No need for life support. No need for food. Just pure information traveling through space. The ethical implications are staggering. Is a digital copy truly you, or just a duplicate while the original dies? Each proposed solution reveals that interstellar travel forces us to confront not just engineering challenges, but profound questions about human identity, mortality, and what we're willing to sacrifice for exploration. Part 8. The breakthrough that might change everything. In 1994, physicist Miguel Alcubierre proposed something shocking: a mathematical solution to Einstein's field equations that might allow faster-than-light travel without violating relativity. The Alcubierre drive, as it's known, doesn't move the spacecraft through space. Instead, it contracts space in front of the ship and expands it behind. The spacecraft rides a wave of warped spacetime. To an outside observer, the ship would appear to exceed light speed, but from the ship's perspective, it's moving slower than light through locally warped space. The catch? Building an Alcubierre drive would require negative energy, something we don't know how to create. The theoretical energy requirement is equivalent to the mass energy of Jupiter, and we need to somehow generate and sustain this impossible state across enormous distances. Is it possible? Technically, nothing in Einstein's equations forbids it. Practically, we can't even imagine the engineering. Yet this is precisely what makes the problem beautiful. A century ago, space travel seemed impossible. Today, we launch spacecraft routinely. Could the same transformation happen with interstellar travel? Some physicists believe that a civilization advanced enough to harness stellar energy might eventually crack the mathematics of extreme space-time manipulation. They might develop propulsion systems that make our fastest rockets look like horse carriages. If that's true, the universe isn't sealed off from us. It's waiting. Part 9. Alternative Futures. What happens next? The future of interstellar travel will likely follow one of three paths. Path 1. Robotic exploration. Instead of sending humans, we send AI-controlled probes and telescopes. Robots don't need oxygen, water, or psychological stability. A spacecraft crewed by artificial intelligence could travel for millennia without complaint. We could explore the galaxy through the senses of machines. Path 2. Breakthrough propulsion. Technological acceleration continues exponentially. What seems impossible today becomes routine in 200 years. Fusion, antimatter, or completely